Hello, today we are taking one more look at zeros of polynomial functions. Really, most of the stuff that we're looking at today we've already covered in previous lessons, so it's a bit of a review. The fundamental theorem of algebra says that every polynomial of degree n, where n is greater than 0, has at least one root in the complex number system. So that's a new theorem we're going to talk a little bit about. We have already talked about complex zeros occurring in conjugate pairs. So if there is an a plus bi, there is also an a minus bi. We've already talked about the rational zero test, which says to find all possible rational zeros, you're going to take the factors of the constant and divide it by the factors of the leading coefficient. So we're going to put some of these into play and just do some practice here with 1 and 2, and then move on to getting ready for our test. So the fundamental theorem of algebra, why is that important? It's important because this theorem actually allows us to be able to express any polynomial with real coefficients as a product of linear and quadratic polynomials. So in other words, we can factor it into linear and quadratic polynomials, and they're all going to have real coefficients. So that's really the purpose behind the fundamental theorem of algebra. We already talked one more time, I guess, complex zeros come in conjugate pairs. So if there's an a plus bi, there's an a minus bi. So if there's a 2 plus 3i, there's a 2 minus 3i. So just remember they always come in pairs. The rational zero test, you take the factors of the constant term, that's the number at the end of the polynomial in standard form. You take all of those factors, remembering the plus and the minus, and then we take the factors of the leading coefficient, which is the number on the degree term, the highest power of x at the beginning. And that list of rational zeros gives us a place to work from if we need to use division to find actual roots. And so we can use division as a tool for factoring. All right. So now we're going to work through these three examples. So A, B, and C, and the directions say to find the zeros. And we're going to use any methods in our toolbox to be able to do that. So it could be factoring, could be completing the square, could be quadratic formula, could be division as a factoring tool. Any of those things that are going to break that down into the zeros. And remember, you can have a zero or a solution and not have an x-intercept. So we're going to be definitely leaving our answers as x equals to represent those zeros and solutions. So the first one we're doing is y equals x squared minus 6x plus 9. When you look at this, you can definitely see that's quadratic. So what we want to think is, what are some of the ways we can solve a quadratic? We can factor, we can complete the square, we can use the quadratic formula. So since this was a perfect square, I know that that's going to simplify to two of the same binomial, because that's x squared, that's 3 squared, and we can look at how that affects the middle term. So when I factor this, I get x minus 3, which is to the power 2. And notice that we switched from the y to a 0 because we're solving. So we're in graphing kind of form here. Now we're in solving form right there. So I factor my trinomial and I get x minus 3 squared. So what I did at that point, take the square root of both sides so we can eliminate the power of 2. And that means when I introduce this, notice in this line right here, there isn't a square root to be found. And now I've introduced that into the problem, so I need to remember to introduce the possibility of a plus or minus solution there. So really, I'm just moving the 3 to the other side, because if I add or subtract 0 from it, I'm not going to get anything. So this is my root at x equals 3. Remember right here that had a power of 2? Well, that means that I have a multiplicity of 2 at that root, or I have two solutions that are both x equals 3. And if I look at the degree in this quadratic is 2, which tells me I should have two solutions, which means I have two solutions because I have 2x equals 3. Question B, I'm being asked y equals x cubed plus 4x. So the first thing I should recognize right here is it's not a power of 2, so it's definitely not quadratic. It's in fact a power of 3, which means that, it has 3 solutions, right? That's what that degree tells me. And remember that solutions can come in imaginary form or complex form. It can be a combination of both, but don't forget complex numbers always come in pairs. So if this were the case and I had one pair complex, then I'd have one more solution to find that might be in the real set. All right, so the first thing I would do here is I notice that it has an x in common. So I set it equal to 0 because now I'm solving and I'm finding the zeros or the solutions. And then I would factor the x out, take out the GCF, and I'm left with this. So this is not a linear factor. This is a quadratic factor, and this is a linear factor. So we know when we have all factors, we can set each factor to 0. So I take x equals 0. That's what you're seeing right here. And then I take x squared plus 4 equal to 0, which is what you're seeing right here. So this is what I need to solve. I need to solve for x. So I move the 4 to the other side, which gives me a negative 4. So when I take the square root of both sides, remember plus or minus, because I'm introducing the radical there. And the square root of 4 is 2, and the square root of negative 1 is I. And we always put the I to the back of the term. So here's my pair, right? If there's a positive 2i, there's also a negative 2i. And so this is 2 solutions. There's the third solution over here. A total of 3 zeros matches what I should know about the degree of the polynomial. Part C starts with x to the 4th minus 1. And I always get students that go, oh, that's not factorable. But really, that's a difference of squares. Remember, we learned when we multiply like bases, we add the exponents. So when I'm thinking about factoring this, I need to think, what plus itself gives me 4, because I'm multiplying like bases of x, which means I would be adding the exponent. So exponents need to add up to be 4. And if I want to break it apart as a difference of squares or break it apart like that, then I need it to be of the same number. So 2 plus 2 is 4. So I put one of the x squareds here and one of the x squareds here. And now I know that I'm difference of squares, so I'm going to take what times itself gives me 1. That's 1 times 1. 1 is a plus, 1 is a minus. So that's how that factor's looking like that for difference of squares. So right now, this one doesn't factor down anymore, but I can go ahead and solve it to get my zeros. This one does factor down further. That's a difference of squares again. So what plus itself gives me 2? 1 plus 1 gives me 2, so that's where the x's come in right here. What times itself gives me 1? That's 1 times 1. 1's a plus and 1's a minus. So this difference of squares again breaks down to this. So now I have all factors set equal to 0, because remember that was the first thing we said we would do. And now I can set each factor equal to 0 to find the solutions. So over here I have x squared plus 1 equals 0. I move the 1 over, it becomes negative 1. I take the square root of both sides, and so I get x equals plus or minus. I have to introduce that because there's no square root up here to begin with. And then I have an I, because that's the definition. Then I can set x plus 1 equal to 0 because that's the next factor. So x equals negative 1 when I move the 1 to the other side. And then I can set my last vector, x minus 1 equal to 0, move the 1 to the other side. So I have 2 complex solutions, which we know come in pairs. And then I have the solution 1 and negative 1. So there are 1, 2, 3, 4 solutions here, which match up to what we know the degree tells us about the polynomial, which is that we should have 4 solutions. We also know that complex numbers come in pairs, so you can see here's my pair right here, plus I and minus I. So you have to be able to use all the tools in your tool bag, and we're going to look at the next problem so we can use and apply some of that division stuff that we've been working with. Okay, so problem 2, write f of x equals x to the 5th plus x to the 3rd plus 2x squared minus 12x plus 8 as a product of linear factors and list the zeros. So linear factors, remember, those are like a line, x plus 2, x minus 2. And so when we get this and it's all in factors, then that should be the case. All right, so the first thing we look at this and we go, I don't know what, I can't factor it. It's bigger than 4 terms. I don't have any factors that they're giving me to find the other term. So that's where the RZT test comes in. So I take the factors of the constant, which is the number back here, and I divide it by the factors of the leading coefficient, which is the number right here in front of x to the 5th. So I'm going to take all the factors of 8, plus and minusing, and I'm going to divide that by all the factors of a, which are plus or minus 1. So my RZT test looks like that. So over here I have 8 numbers, possibility, rational, zeros that I can use. And so I start plugging them in to the function right here until I get a 0. So I plugged in negative 1 and I got 2. I don't really need to know that I got 2. I just need to know that I didn't get 0. So when you're plugging in a number, when it becomes evident that it's not going to be 0, you don't need to finish it out. You could just say f of -1 does not equal 0. Okay? Then I plugged in 1. And when I plugged in 1 to this model up here, I got 0. So that tells me that that is a factor and that the remainder is 0. So I go to my synthetic division, and that's the thing about rational zero tests, is these are all going to be linear roots, so you can always use your synthetic here, pretty easy. So I put all of my coefficients in, paying special attention to put a 0 in for x to the 4th, because that's missing in my progression down to 8. So there's all the coefficients. I'm dividing by 1 because that's what I found here when I looked at the rational zero test. And so I brought it down. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 1 plus 1 is 2. 2 times 1 is 2. 2 plus 2 is 4. 4 times 1 is 4. Negative 12. Positive 4 gives me negative 8. Negative 8 times 1 is negative 8. 8 plus 8 is 0. So I did get that 0 remainder just like I knew I should from where I used my rational zero test and I used my factor theorem. And this right here is the other factor. So here's what we now know. We know that we have a factor of x minus 1 because that's what divided in there evenly. And remember, this is the root and this is the factor. So we got to go back to factor. And then the other factor is the quotient that we got as a result of the division. So I can write out my quotient. So then the next thing I'm going to do is check this and see if it's factorable. And it's not because it's 5 terms. So we use division again. But luckily for us, notice the leading coefficient is still 1 and the constant term is still 8. That's the exact same combination I used in my RZT test up here, which means I don't have to create another RZT test. I can still use these numbers. When this breaks down, if that constant or that leading coefficient had changed, then you may have to write out a new RZT test to be able to do this part. But always check back to the original and see if it's possible to still use the same one that you made in the beginning, which it is. So then I started plugging in numbers, and I plugged in a -1, and I said, yeah, that's not even going to get me anywhere near 0. So notice how it's just not equal to 0? That's totally fine. Don't need to know what the number is. Just need to know that it's not 0. When I plugged in a 2, that wasn't 0 either. When I plugged in a -2, and when I say plugged in, I'm talking about putting it right in here. -2 to the 4th, -2 cubed, 2 times -2 squared, 4 times -2, and the -8. All right, so once I plugged that 2 in there, I got a 0. So this tells me this is going to be the remainder of 0 means I have a factor at x plus 2. So I use the root to do my synthetic division and break it down. So here we go. -2 goes right there. And then I wrote all the coefficients from here. There were no missing powers, so I don't have to put any zeros, and away we go. 1 drops down. -2 times 1 is -2. 1 and -2 is -1. -2 times -1 is +2. 2 and 2 is 4. +4 times -2 is -8. 4 and -8 is -4. -2 times -2 is +8. -8 and 8 are 0. So yes, we know we should get the 0 because we already found that when we plugged in. That's how we knew what number to divide by. And then right in here is the coefficient. So now my factorization, I have the -x minus 1 from the first division. I have the x plus 2 from this division. And then I have the quotient, which we got under here as a result of the division, and I put it right there. So again, when I get to this point, I'm checking, can I factor and see if it's going to let me break that down. And fortunately, it becomes factorable at this point, so I'm through needing the division. I can just factor by grouping. So I grouped these two together, and I grouped these two together, and I pulled out an x squared from the first part, leaving me with an x minus 1. I pulled out a 4 from the second part, leaving me with an x minus 1. So this factors to x minus 1 times x squared plus 4. All right, so we get to here. Notice it's still set equal to 0 because we're solving. And the tendency here would be to stop because you can't factor or break it down any further. However, remember the directions were to write it as linear factors, and this is most definitely not linear. So in order to figure out what that linear is, I'm just going to set this factor equal to 0 and figure out what the solutions are, which would be plus or minus 2, and work my way back to a factor. So if this is a positive 2, when I go back to the other side, it would be x minus 2. Remember right here, it's x equals 2i. So when I move the 2i back over, if it was positive here, it goes back over as a negative. If it was negative here, it goes back over as a positive. And so these are actually the linear factors from here. So you have to pay attention to what the question is asking you to do. So if it's just asking you to factor it, then this would be okay. But if it specifically says nonlinear factors, then you need to make sure that you take all of these, even though they're going to be imaginary, and create the roots or the factorization, which is this. Okay, so let's talk about this. We have 2 of these. We have 1 of these, we have 1 of these, and we have 1 of these. So if I'm listing out my factors, I have x minus 1 as a factor, x minus 1 is a factor, which is x equals 1. And then I have x plus 2, which is a factor, so then that is x equals negative 2. I already have that one over here. And then I have the plus or minus x equals plus or minus 2i. So this one has a multiplicity of 2. There's 2 roots at x equals 1. This has a multiplicity of 1. There's 1 root at x equals negative 2. And then I have my 2 complex. If you notice, there's no multiplicity listed over here because in order for it to cross the x-axis, it would have to be something like x equals negative 2. Here is plus or minus 2i, and imaginary numbers are not on the real number axis. So these solutions are happening elsewhere in the graph, and they're not going to touch or cross at the x-axis here. Therefore, they're not going to have a multiplicity at the axis there either. So you can see how we use the technique of division and factoring kind of combined throughout this problem to work it out. We will be reviewing next period and getting ready for a test over polynomials. This is the last section that we will be covering. Thanks, guys. Have a good evening.